Hello students, in this video we will be studying the second type of semiconductor detectors, which is the surface barrier detector and scintillation counter. So first we move on to surface barrier detector. This is the second category of semiconductor detectors. It is a widely used surface barrier detection. It is a silicon surface barrier detector. A typical surface barrier detector is shown in this figure. It consists of an extremely thin p-type produced on a high impurity n-type silicon wafer. So you can see this is the n-type silicon wafer and a thin layer of p-type is produced on this high impurity of n layer. The combination constitute a large area of p-n junction. See the p-n junction diode. To construct the detector, an n-type silicon wafer is taken and on its surface is etched with acid and exposed to air. Here you can see an electrode, front electrode, and this is the back electrode connected to the positive terminal. Ionizing particle enters in this region. Now, an oxide layer is formed on the etched surface and this layer acts like a very thin p-type material. Under the influence of an externally applied field, electrons will be swept towards right and holes to the left. As a result, an immediate volume around the interface will be cleared of carriers of both signs and a depletion layer will be formed. The passage of an ionizing radiation will create electron hole pairs which will be swept towards the appropriate electrodes by the applied field, and a pulse will be obtained to signal the passage of the ionizing radiation. Good electrical conducts are provided by evaporated thin gold film on the P surface and a thin aluminum film on the N-type silicon layer. These detectors have a long stability, small size, negligible absorption, and linear pulse response over a wide range. Next is scintillation counters. This is one of the earliest form of radiation detectors which is used extensively by Rutherford and his colleagues. There are some substances known as phosphors which emit light flashes when charged particles, X-rays or gamma rays pass through. So we make use of phosphors in these counters. Phosphors. These substances are called scintillators. The momentary flashes of light emitted are called scintillation. The ZNS activated with traces of silver, the organic crystal anthracene stability, NAI activated with thallium are some examples of phosphorus. In older days, the visible scintillation produced by the incident radiation were observed. They were physically observed and counted through the microscope fitted with a screen coated with phosphor. This was a very tedious process to adapt. It required a period of adaptation of eye within the dark room. ZNS was the phosphor used by Rutherford for the detection and counting of alpha particles. Nowadays, very high-speed electronic devices have been developed for detecting scintillation taking place in times of order of nanoseconds. Besides the detection of charged particles like alpha, beta, high-speed protons, neutrons can also be detected by the scintillation counters. This method has been found to be especially useful for gamma ray detection with high efficiency. You can see the schematic diagram in the next slide. Here, a nuclear radiation falling on the scintillator can dissipate all its energy in it if the dimension of the scintillator are large compared to its range. The scintillators produce scintillations or the light pulses which reach the photocathode of a photomultiplier tube which is optically coupled to the scintillator. The photomultiplier tube consists of photocathode and several diodes, maintained at successively higher potentials of about 100 volt per dynode stage. When light pulses reach a photocathode, emits photoelectrons. This photoelectrons emitted by the photocathode is accelerated by the electric field to the first dynode, where it produces a bunch of secondary electrons. These electrons are accelerated to the second dynode and produce more electrons. This process is repeated at each dynode. These are usually 10 or more. There are usually 10 or more dynodes which ultimately achieve a gain of 10 raised to 7 to 10 raised to 8 by the time electron reaches the last stage called the anode. When it reaches the anode, it will be multiplied this much times. Okay. Now the magnitude of the output pulse from the photomultiplier is proportional to the energy of the particle incident upon the phosphor in a given scintillation counter. These pulses are fed to the pulse multiplier amplifier followed by a scalar circuit. So here you can see the nuclear radiation coming on the scintillator, light reflector. This is a photocathode. Here it receives, and here is the multiplication of or more number of secondary electrons are produced using these dynodes. And here you can receive the final amplified electrons at the anode. And here you can see it to the outside it is collected or detected. So, now what are the advantages? It is a much higher counting efficiency for gamma rays due to the greater amount of energy dissipation by gamma rays. It offers greater stability, greater accuracy, shorter resolving time and higher efficiency than GM counters. Now the applications. Scintillation counters can be used to measure the particle energy. Because of their rapid response, they are used for the accurate timing of nuclear particles moving at very high speed. They are used to detect detection of antiprotons also. They are used in the study of cosmic rays for the detection of mesons and other unstable particles of high energy. These are the applications.